coming along. My name's Dean Hillan. I work at Paperless Post, which is a startup down in Fidye in Manhattan. And our thing is greeting cards. You jump online, you can create greeting cards, wedding cards, that sort of thing. Customize it all online, send them either via email, or unlike the name Paperless Post would suggest, you can actually get a paper copy of the card. So I've been working there about 8 months or so. Before that, I spent way too long in university doing research, mainly programming things like MATLAB and wasting my time on Fortran and IDL and stuff like that. Last few years, I found Python though, and I've never really looked back since. And for me, one of the best things about Python is it's always my go-to language for just prototyping something crazy or just trying out some ideas. The community and the support and the libraries just make it such an easy way to just try out something and have fun with it. So hopefully everyone gets out of this talk, just have a bit of fun with Python. As you might hear in my accent, I'm actually Australian, which is why I put a U in color, so that's optional for the audience. I speak the Queen's English. So, as I mentioned, Paperless Post, we do lots of greeting cards, right? So, about 8 months ago, just before I started this job at Paperless Post, I was back with my sister in Australia. She's planning a wedding. So I said, well, you've got to use Paperless Post, surely. And I said, what do you want? Do you want like high-end cards? They work with designers. Do you want Vera Wang? Do you want fine print? Do you want gold embossing, etc.? And she said, no, I want peach and mint. So why peach and mint? Well, that's the theme of the wedding. That's the color themes of the wedding. So I jumped online onto Paperless Post and put in peach and mint, and you get rubbish results. They don't look anything like peach and mint to me. There's even black and white cards in there. So that's a bit disappointing. And the way that the search works at the moment is basically people get in there and manually tag the cards. Like when the designers create these cards, they get in there and say things that's got red and blue and such an object. And this is powered by Elasticsearch, I think. So the side project was, well, how can I find peach and mint? How can you more, describe color in very descriptive terms and be able to actually search the cards themselves to pull out that information? So how are we going to attack this problem? Because color and language are two very deep subjects in themselves. So like with all problems in life, the solution comes from XKCD. Everyone reads XKCD, I hope. If not, that's assigned homework. So a couple of years ago, he ran this survey on XKCD where he wanted to get people to describe what they thought the color was, how they'd use language to describe it. So you would just serve up a color and people put in what they think it was. So it was over 5 million colors were named this way over like 200,000 sessions. And basically you just keep serving up colors until people basically lose their mind. You can see here there's a bunch of different slight variations on green. Am I skewing your results? 25 in a row is too many. My favorite one's down here. Day 3, sanity lost. Colors keep changing. What do you want, Mr. Green? So he ran this for a while, and all the results are online. And if you go download them all, turns out there's about 950 in the list that he compiled. To that list, I went through and added any of the ones from where I work, Paperless Post, any of the palette colors that the designers work with. I added in another couple of hundred on top of that. So now we've got a list of about 1,100 different colors, described like things like this: cool gray, darkish purple, flat blue, etc. And he gives next to that the hex code for the color. So to go from the hex, we can go into RGB space, which is described in this like color cube, which is 256 on each length of the cube, described by the R, G, and B red, green, blue triplet. So that's easy enough to convert that over using struct in Python. So we just go through that list, convert all the hex code straight into RGB. So now we're dealing in this RGB color cube. That's not the only way you can describe color. It can be in other color spaces, but for the purpose of this prototype, we'll just stick to RGB. So if you look at that, this cube, the colors you're seeing on this are at the far ends of the cube. So if you imagine the 6 faces of the cube each have like a saturated in one of the RGB different colors. So if you look at this next map that the XKCD guy have created, I can't really see that very well off the back probably, but he's mapped the saturated faces of the cube and sort of unfolded it, and then said, what people mainly call these what I'm going to call like a superset of colors. These are more broader descriptions of colors using things like just green, blue, purple, pink. So for any of the colors that are in our list that don't already have one of these sort of super descriptors or a more broad description of color, I went through and added it in. So for example, if you know to look for dark sage, which is like a greeny color, that's great. But if you're like me, you're probably not going to be searching for dark sage specifically. So what I've done is added green to dark sage. So things like coral pink, that's already got one of these super descriptors appended to it. So we need to leave that one alone, that's all right. If you get to things like dark sage, well, what is the closest color to that one? That would be a green. So I've added that, so now it's called dark sage green. So if I just want to search for green, I can still get to these results that are under the dark sage umbrella. Okay, so now we need to map all the colors in our color cube to this list of colors. So to do that, we've got this array of 256 by 256 by 256. So we're going to step through every point in that RGB cube and then figure out which of the color names in our list of about 1,100 most closely, whereas in say like a Euclidean distance, what is closest to the one in the list. So for that, we've got the 256 by 256 by 256 array, and we're going to match it up to all these different ones in the color list. So for example, if we're over in like the red sort of end of things, where we've got 255 for red, and then 1, 1, as we keep going down, 1, 2, 3, 4, 5, 6, 7, we switch from going to fire engine red to bright red. So that's when the distance is flicks just over to the next closest color. And the way you can implement that, at least the way I did, is you just set up an array where you're going for red in 256, same for green, same for blue. And then you take that red, green, blue triplet and make it into an array of the same size as our color list. And then you can feed that straight into a function here, calculate color distance, which is just basically the square root of x squared plus y squared plus z squared. I'm talking about like a Cartesian distance between pixels here. You just feed those two arrays in there, and it will spit out a distance between each of the colors to that RGB triplet that you're currently sitting at. And then it's just a matter of searching for the minimum distance and then setting that in our array. And so this takes a couple of minutes to run, at least on my laptop anyway. So once that gets to the end, you might want to pickle that. So that's a way of just storing the object to the computer so you can load it back up into memory rather than having to compute it every time. Okay, so if you go and pull all the cards off Paperless Post, at the time of this presentation, there was about 6,500 of them. And now for every pixel in every one of these cards, we're going to use that mapping that we've created, that color lookup table, to map each one of the pixels to one of these 1,100 colors. So imagine we've got an array with 6,500 rows and 1,100 columns, where each of those columns is one of the color names. And as we step through every one of the pixels on every one of these cards, we're just going to bin the pixels and add counts to the different color bins as we go through. So we end up with a 6,500 by 1,100 array. And I'm calling that our image corpus. And you'll start to see as we go a bit further on, there's sort of this connection between sort of natural language processing and talking about this stuff in terms of like documents and words rather than just colors, because we're trying to make this connection. All right, so we've got this array we just generated, the image corpus array, which is really a count of the color frequencies. And we've got our 1,100 list of color names. Now, if we want to be able to search on those names, we need to break them apart into the vectors. We need to be able to break like multiple words that describe a color into the unique vectors across our documents. Because what I mean by that is we can use a count vectorizer, which comes out of the scikit-learn library. And we're going to use this count vectorizer to figure out what are all the unique vectors in our list of color names. And we can use things called n-grams, which is where you consider one or more words at a time. So for example, in our vector list, if we had a color which was fire engine red, when we go to create our vector list, we will now have fire engine and fire engine red become vectors that will be searchable. So when you do that, you end up with this thing which is now 1,100 rows by, say, 1,700 columns, which contain all the vector information for all the words you pulled apart. So is what that thing would actually look like is if you had, you're at the color was fire engine red, and across your vectors you had, green, yellow, blue, a bunch of different words, and then fire engine and red. That first row would look like 0, 0, 0, 0, 0 until you got to the fire engine, which would have a 1 in there, and then red, and then have a 1 in there. So it's doing a count of which vectors link up to which color names. Okay, so now we want to be able to get from here, which is where we can actually search for the color names, and map this back to our image corpus, which has the counts of all the different colors. So to do this, we just matrix multiply the image corpus, so this thing up here, by this one here, that thing. The inner dimensions agree, so what you're going to end up with is a 6,500 by 1,700 array. And then we're going to perform on that something which is called the TF-IDF transform, and that stands for term frequency inverse document frequency transform. As what that does is, because we've got a bunch of different colors which exist in cards, and then those colors might exist on other cards as well, if that color occurs a lot on one particular card, we want to push this up the ranking. If you're searching for red, those are the sort of results you want to get, where there's lots of hits of red on that card. But if red occurs across a whole bunch of cards, or maybe a better example would be white, you'd see a lot of white cards. If it's not unique, then you want to push the ranking back down, and that's what the inverse document frequency part of this transform does. So if it occurs a lot, and it's unique among the corpus, that's where you want to rank things highly, and that's what the TF-IDF transform does. And so that would look something like this. This is doing our first matrix multiplier. The color name vectors, which we calculated previously, where we use that count vectorizer from scikit-learn, that returns a sparse matrix. So you need to convert that to array, and then you do the matrix multiplication on that. And then we import from scikit-learn the TF-IDF transformer. And then it's very simple just to go .fit transform. If anyone's ever done any machine learning type stuff with scikit-learn, it follows the same syntax. It's really easy to apply that transform. Okay, so now we have a mapping using this thing here that goes straight from all the color information in all the individual cards into searchable word vectors that someone can put in, and then we pull out the most high-ranking results. Just as like a quick worked example, this is actually one of my co-workers' GitHub pictures. But to me, it actually looks like a 4x4 picture. So if we treat each of these like pixels, in this row, these rows and columns here, this is what the RGB triplets are for each of the 4x4 pixels in this thing here. And you'll see that this one here, which is this guy, is the same as this one here. So it's that one and that one. And if we use our color lookup table and convert to what is the closest color description from the XKCD survey, you see we get these things like wheat white up in the top left, lots of grays, sage grays, bland grays, medium grays. You can see medium gray comes up twice in here. And so now when we take this, if we were to insert this picture amongst all the paperless postcards, run the full matrix multiplication, do the TF-IDF transform, then the words that would best describe that picture would be things like this, starting in the top left: dirty purple, gray, dirty purple, dusky purple, etc. So if you're going to, say, populate the things in Elasticsearch with color terms which would describe the different cards, you might take, say, the top 20 of these colors which describe that card and then decorate your Elasticsearch JSON that way. So this is what happens if you do a search for gray, dirty purple amongst all the paperless postcards, and if we had that example picture inserted in there. So you see this does a pretty good job of getting what I would consider, I guess, dirty purple. And the first one that comes up there is this guy's GitHub picture. So it worked. And so just to remind everyone, the whole idea was to see if we could get at things like peach and mint. These were the original results. But now, if we search on this new system, this is peach and mint. No wedding cards, but I think it does a much better job. And so now you can really have fun with it. You can get really descriptive with the color. Things like red brick banana. Which kind of looks like children's cards or birthdays or something like that. Or if you want to go for the more elegant light grey oyster metallic gold foil, probably a better chance of pulling out a wedding card or something like that way.
Does foil match anything?
So if it's in that XKCD list of color names, there would be some sort of, I think there is a gold foil color or something in there. And also Paperless Post, foil is one of the high-end card things you can get. So I think it's among the color palettes there. So how this whole thing could be improved, we go for a more formal description of color rather than just using this XKCD survey. It does a pretty good job, but there are a bunch of weird colors in there if you sit down and have a look. Things around baby excrement and stuff like that. We don't necessarily have to use the RGB color space. It's a convenient thing when you want to calculate the distances between colors. You're using a Cartesian distance, square root of x squared plus y squared plus z squared. Whether that necessarily relates to a proper distance in the color space is debatable. But maybe you'd like to move to different representations of color space, which are these cylindrical coordinate systems. And then, of course, what we really want to do is be able to combine the different colors you're searching with the actual content in the card, which would be something that happens with an integration with the Elasticsearch, which is currently powering it. So now just the old shameless plug for the company you work for. If you guys want jobs, we have jobs. You might see some Ruby in there, but don't hold that against us. Yeah, feel free to reach out to me with an email, or if you want to be really disappointed, you can follow me on Twitter. I think my first tweet ever was at this conference a year ago. So if you'd like yearly updates on Pi Gotham, feel free to follow me there. And I have this thing here. Let's see if we can run a little demo. So these up here is a bunch of these colors that come out of the survey. So we could go something like this. It's hard to do. It's not mirroring on my screen. I've got to go off this. All right, let's put that in here. There we go. Apricot. Works pretty well. I think I was playing with eggplant earlier. Has anyone got some colors they want to search for? So how do you spell that, though?
It's F-U-S.
I think this was on the survey itself, complaining about no one knows how to spell it. F-U-S? Is that the one? Cool. Is that Fuchsia? I don't know. Seems legit, yeah. Anyway, so in summation, Python is heaps of fun, and there's so many powerful libraries out there to help you just try any crazy idea you've got. So I really hope that we can get this integrated one day. Anyway, thanks. Good time for questions? Yeah.
So how do you distinguish between color and palette? So you're putting in two color search for two different colors, maybe, or one or two, and then is that considered in your schema the predominating color, and then everything else is cool, as long as you've got that color in a certain area?
Yeah. So I guess the first thing that would take care of that is this TF-IDF transform, so that if you're searching for two different colors, and one of those colors happens to be a unique one amongst the corpus, and it occurs a lot in certain cards, then it's going to try to bring those ones up. The second part, which I didn't really go into, is how I'm actually doing the search part of it. Like you put in the word terms. As what I'm using is this thing called you might see a bit of code in here, called a cosine similarity. So what that does is, if you've got, let's say you've got cats and dogs in your document, you've got this two-dimensional space of cats and dogs. You've got cats on the y-axis and dogs on the x-axis. And you've got some cards in there which are basically documents which have a high count of cats and a low count of dogs. So it's a very steep vector in 2D space. And you've got some other ones which have more dogs than cats. So the vector would look more like that. When you do a search for cats, that vector looks like it's just along the cat axis, the cat y-axis, right? And if you do a cosine similarity against the search and the 2D space, it's looking for the distance, the angular distance between the two vectors. So it will, if you're looking for the smallest distance between the two vectors and you're looking along the y-axis and you've got this other one here which is rather close by, the cosine similarity will give you a measure of the angular distance between those two. And then I'm trying to return the minimum angular distance to the closest search. So I hope that sort of explains a bit of it. It's a bit complicated. Anyone else? Yeah.
So you get the color name based on the RGB color space. If you change it to the art color space, how will it be transferred for this kind of naming system?
So to move to a different color space, I guess the key thing there was when we're calculating the distances between, say, the color list we've got a color list and RGB triplet. You could convert it to the HSL or the HSV color space. And then you need to figure out for each element in that color space which is the closest name descriptor. So at the moment I'm doing this Cartesian calculation. I'm trying to minimize the distance in the square root of x squared plus y squared plus z squared. If you move to something like HSL or HSV, I think that's a cylindrical coordinate system. So your distance vector has to change. You've got to calculate that differently. I'm not sure how that would affect the results, though. Yeah, I just have to try it, I guess. I don't want to stand between people and coffee. So thank you.